Good afternoon, everyone, and welcome to the webinar in Artificial Intelligence and Machine Learning in Space. My name is Adrian Saez, and I am here in representation of iSpaceSchool.com. Before we start, I would like to thank Alessandro and Giovanni from Neuronet.blog for the webinar and remind you the possibilities to extend the training related to artificial intelligence at iSpaceSchool.com. Alessandro, the floor is yours.
Hello, good afternoon. Thanks for having me here and my colleague Giovanni Iannone. So, who are we? So, my name is Alessandro Migliaccio. I'm a chartered engineer with the Royal Aeronautical Society in the United Kingdom, and I work as systems engineer at Airbus operation in the UK. I am an expert of metal fatigue, aspiring futurist, and I worked for more than 10 years in aeronautical companies. I lead projects that have to do with big data, data analytics, and a little bit of machine learning. And for the last 10 years, I worked together with my colleague and friend, Giovanni Iannone, to write down, to codify the merger between artificial neural networks and systems engineering as a discipline, and that will result in a book. And I will tell you more about it at the end of the presentation. Giovanni is an aerospace engineer as well. We worked for several years together on aeronautical project. He's an expert of airworthiness and fault analysis, and he worked in different companies and government agencies as well, and is also trained in the USA in systems engineering. So I think it's enough to talk about us. Let's go to the topic of this presentation, which is artificial intelligence. So we're going to move from the definition of artificial intelligence to talking a little bit about systems engineering, machine learning, and then we'll get to the part about artificial neural networks and space robotics, and in general about what are the challenges connected with AI in space. You'll see that everything will flow organically from one topic to the next. So please stay with me, to follow the flow, and keep your questions for the end. Thank you. So let's get on with it. So what is artificial intelligence? There are many different definitions of artificial intelligence. I'm not an academic of artificial intelligence. As I said before, I'm an aerospace engineer. So the way I see it is, artificial intelligence evokes different images in people. People of my generation may think about some kind of future scenario with robots taking over humanity. Some other people may think about the philosophical, metaphysical side of artificial intelligence. And some other people must have seen the cute videos from Robot Dynamics with dancing robots. So there are different aspects to it. In the common perception, I'll say that the easiest definition is talking about systems that think like humans, that operate like humans, that think rationally and operate rationally. So there is two aspects to it. There is the part about thinking like human. First of all, what is a thinking system? So what is an intelligent system? We're going to see it in the course of this presentation. And what does it mean to think rationally? How a machine can make decision, how they're going to make their decision based on the available data is also going to be a topic of this presentation. So let's say the creation of a system that mimics human behavior is one of the purposes of artificial intelligence, if not the main purpose. If we go on to the next, you can see that artificial intelligence is a combination discipline in a similar fashion to aerospace engineering, which is a combination of chemistry and solar panel technology, electronics, and artificial intelligence, and so many other things. The same thing is for AI. So it's a combination discipline that has in it a lot of different others. So how are those organized? So you must have heard about robotics, deep learning, machine learning, so and artificial intelligence. How do they connect? So basically, all these disciplines, they all make the wider context of artificial intelligence. So artificial intelligence can be seen as any technique that enables machines to mimic human behavior, as I said earlier. So machines that behave or solve a problem as their human counterparts, if not better in specific domains. Machine learning is a more recent discipline, started in the 80s, and is a subset of AI, which uses statistical methods to learn without being explicitly programmed. While deep learning, it's a subset of machine learning that deals with, uses multi-layered neural networks to learn from large amount of data. And to satisfy your curiosity, we're going to touch upon neural networks in one of the next slides. So this just to give you context, but if you Google it, you'll find a great deal of different ways that these disciplines can be organized and connected to AI. Really a great deal. So I challenge you to go out and find different organization of the topic and form your own view. So we can move on to the next. So I put like a little bit of a cute, illustration of how machines may think. So artificial intelligence can't replace human beings in every way, but can do it in a specific working environment. And the environment in which the AI is going to operate is very important, because for an AI to work correctly, it needs to be programmed with environment variables in mind, but it needs to be able to adapt to changes in the environment. It needs to be able to deal with uncertainty, which is different from a teleoperated robot, for instance. That's not an AI, it's teleoperation. So when there is a level of autonomy, we are talking about artificial intelligence. So that the machines or systems, let's call it more generic systems, that can work on their own. And how does an intelligent system see the environment or perceive the environment? Through a number of sensors, and acquires a great deal of data that uses it as a base for its decision making, together with information that has been pre-programmed and training that is being given by its human designer. So as we said earlier, so an AI takes as an input, it operates using, understanding events, working in a specific environment. It has a number of pre-programmed heuristics or guidelines to determine its behavior. And this all connects, to, humans work in a similar way with ideas. But what's an idea? There are different theories about what's an idea. Plato's theories seen an idea as something universal that is somewhere else, is not reachable by people, and makes the difference between an opinion and knowledge. The idea is in between. And of course, all of this information, this heuristics, sensor information, needs to be discretized and put in a form of a number, so that according to the theory for which everything that is can be perceived can be translated or discretized into numbers, and that mathematical formulas, equations can explain everything about the world. So an AI used all these concepts to perform its function. And what's the purpose? So it can use it to solve a classification problem, which could be for instance, a spacecraft needs to follow an asteroid. So it needs to be able to tell if what it's seeing is an asteroid, or is the background of space, or it's a star, or something else, or another spacecraft. So classification is very important. Decision making is also a function of AI. So the crunch basically all the data, and based on the of their own heuristics, determine or give recommendation on the following action to take. And that connects also to foresight. So AIs can, if properly programmed, predict what's going to happen in the future. You say, okay, if humans can predict the future, well, foresight and forecasting are two disciplines that are science-based, so they use a great deal of historical data and current data to predict future trends. And that can be done automatically by an AI. So we can move on to the next topic. So where are we operating? You know, an AI is not going to replace a human brain. It works a little bit at the intersection. So what we are talking about, it's really the intersection of different disciplines. Artificial intelligence, the span of activity of possible functions of a human brain, which is enormous and not fully understood, systems engineering, and what I told you before about foresight, decision making, and classification. Maybe I didn't talk enough about systems engineering. Systems engineering is a multidisciplinary approach that deals with the conception, design, production, operation, and ultimately disposal of a functional and effective system. Systems engineering is a little bit of the framework, you know, the architecture of our system. So how to design the system, starting from its basic elements, and predict how it's going to work in its operational environment. This discipline applies to every field of engineering and science, but it's very important for space engineering, because oftentimes what we design is going to operate in an environment that is outside of our control, and for which we don't have, you know, it's like a little bit like an aircraft where there's no possibility of mistake, you know, so because you don't have control over it, so it needs to be, you know, fail proof. And to do that, you know, it needs to be conceived and designed properly for its operational environment. So that's where we're operating. So everything that we say about artificial intelligence must be seen according to systems engineering principles. Yeah, so let's move on to the next. So why do we need the support of a systems engineering approach? Well, because a systemic or systematic approach allows us to understand better our environment. So it allows us to analyze the environment in which the system will operate. And both event and environment are essential components to build our system. In this illustration, you can see what we call the heuristic mountain, or however we want to call it, so that when we program an AI, for instance, we need to go through a number of logic levels to make sure that the machine builds enough heuristics, like a little bit like a human baby that needs to learn, you know, how to operate, you know, learns rules as it goes, and once it reaches the top, so it's got enough logic in it, enough heuristics, then the majority of the work is done, and this is going to be able to operate in its assigned environment in a very efficient way. And at that point, the complexity is also going to go down. Let's say a little bit more on this before we move on. So as we said, you know, every event, you know, so our AI, our system, our intelligence system is going to deal with events. Events needs to be, again, how a machine can understand what's happening. Well, the events can be logical, you know, so explainable through a logical approach. or can be explained by an empirical approach. So according to if they can be demonstrated by experience, or can be deducted by relationship of variables. But everything in the end becomes a computational event. So it needs to be translated into mathematical structure. So facts, relationship, and experiences need to end up need to work within in a computational, create the computational event, and needs to be are addressed by the intelligent system through a mathematical structure that has been inserted in the machine, and it regulates its operation. You'll understand in a minute when I'm going to talk about neural network. But first, what kind of systems are we talking about? We talk about intelligent system. Well, an autopilot is a very simple form of intelligent system because it has a specific objective. So the control of the aircraft without human input. It works within a set of constraints, a flight plan set by the pilot. There are obstacles on the route, and it is its own design limitation or limit of authority. As you know, in your car, for instance, when you set your active cruise control, the car wants to know what maximum speed it can reach. So it will operate automatically within boundaries. Those are the constraints. So it can be design constraints or can be set. And it will operate according to information that it got through its sensors. So an autopilot will get a number of sensors that will allow it to make the right decision in terms of what route to follow to achieve the goal. So is it fully intelligent? It is an adaptive system, I would say. It's not a fully we cannot call it like fully artificial intelligence. Depending, it's all a matter of degrees of complexity. From a simple intelligence to a more complex intelligence, such as the those softwares that can play like the AlphaGo done in London. There's a sophisticated set of neural networks that can beat a human player at the game of Go, just like many years ago was done with the game of chess. Again, so a systems engineering approach will allow us to determine the architecture of such system. So for instance, an autopilot will use a number of sensor information, will use inputs from the pilot, such as the flight plan, and operate on flight controls. So will understand its environment, will use its input from on its what mission is to accomplish from the pilot, and will operate on the flight controls on its own according to its own decision-making algorithm. So again, we are talking about the architecture of an intelligent system. So how do we make our systems intelligent? Well, one way is to use artificial neural networks, for instance, but there are many different algorithms and mathematical structures that can allow us to do that. A neural network, in a most simple definition, is a set of it's a mathematical construct that basically starts with some inputs. So you have input nodes and you have output node. So basically, you give input to the network, you get an output. Now, what the network is going to do inside is complex, but what is important is that the output will have eventually to be what we expect, similar to our target. And how do we get there? By training the network, by feeding to the network data for which we know the output is known, so that the nodes inside the network will be able to readjust and approximate the expected result. You can see in the chart here that basically when the error function is minimizes, then you get new results. So a predicted score, for instance, if we're talking about some game or flight parameters, similar or very close to the real one. So you're going to get convergence. So that means that even when you give to the network new data, an unexpected situation, it will be able to operate in an optimized fashion, a similar way to what, let's say, biological intelligence would do. For instance, one neural network could be determined to determine the price of Bitcoin, for instance, based on historical data. It will be able to approximate the future trend by analyzing, by being trained with a great deal of historical data for which we know already the outcome. But neural networks can come in different shapes and form. It can also be put in networks on networks. So if you want to know more, I will tell you about how to know more at the end of the presentation. So we are getting slowly to more and more into the space domain. So again, reiterate the idea is that a space intelligent system needs to be able to observe and recognize its environment through, for instance, pattern recognition. That are so information from the environment are transmitted, are seen as variables and elaborated through an algorithm that has been already trained, for instance, through a neural network, and gives a specific output. For instance, a spacecraft that needs to grab a piece of space debris. I think you're familiar with what space debris is, just floating scrap metal or objects that are in the Earth orbit. So it will have to recognize a piece of debris and go for grabbing it. In order to do that, it will be fed, for instance, its imaging system will be trained on the ground before the craft is launched with thousands and thousands of pictures of space debris so that it will know what to look for and how to recognize it autonomously when it's in space outside of our control. Or it says here, yeah, without explicit instructions. Yeah. So more and more into the space domain now. So this concept of autonomy, which we hinted at earlier, is very important for space robotics or artificial intelligence used in space. Robotics has to do with the mechanical part most of the times, but really you can use, the most wide definition of space robotics as similar to intelligent systems, in space. So artificial intelligence system operating in space, most of the time they take the form of robots. Examples, robotic arms of spacecraft that oftentimes have a degree of autonomy. Well, the Martian rover, for instance, the different rovers launched that they are not only teleoperated, but they can get as input specific mission, and they be able to determine how to accomplish it autonomously. Other forms of artificial intelligence in space could be the astronaut support, artificial intelligences that are basically working a little bit like our Amazon or Google assistant, and they will do it in space with more information. Those artificial intelligence are very limited. I mean, the one that we use on the ground, because they don't have sensors. These devices, they take information from the environment and they're able to elaborate it and to perform specific function. So, and that's what makes them intelligent. So the ability to sense and to decide what to do without input, or as some of these devices do, take limited input and interaction from the astronauts, and we'll see that collaborative robots are a big part of the future of artificial intelligence, not just in space, but also in ground-based applications. So I'll say let's go to what are the enabling technologies that are going to help us to have a full implementation, an effective implementation of AI in space, which we do have today, but more and more, more advanced in the future. If you want to have robotic system that creates an habitat on the moon or on Mars, we need to equip these systems with high level of intelligence and autonomy. So let's talk about these enabling technologies then. So scalable autonomy. So autonomy, as we mentioned many times, is the ability of a system to achieve a goal while operating independently from external control. While scalability is the property of a system to handle a growing amount of work by adding resources to the system. So scalable normally means, that it can be made in bigger and bigger size or smaller size. In artificial intelligence, it has to do with being able to get data, more and more data, and uses it to create, and to improve its decision making, to learn from the environment. As for the autonomy, I think it's very clear to all of you what we are talking about. That autonomy is essential, because again, some of these systems operate in environments where humans cannot reach or cannot operate safely, and they need to be able to work independently or autonomously. Distributed artificial intelligence in space is also a thing. So in the picture, maybe it's a bit misleading, is the LISA space interferometer. There is a set of satellites that need to operate together to detect gravitational waves. These crafts, they need to coordinate with each other to maintain a certain position and to perform experiments. This is just to tell you that collaborative robotics and AIs that talk to each other and pass data to each other is really at the frontier of what we can do, and it's especially essential in space because we can't launch enormous spacecraft. We can only launch small ones because of limitation, cost limitation, and rocket technology. So it's essential that these constellations or groups of small craft work together. The next topic is the artificial intelligence on the ground. So this can be seen in different ways. The aspect I'm referring to is the ability of different computers to talk to each other to resolve space problems. Like for instance, the picture of the movie I put, where people had to put their brains together to sort the problem of a spacecraft that could not be launched or whatever was the problem in that situation. So the same things on the ground, computers, they need to operate together in a distributed fashion and be able to talk to their counterparts in space, so that they would collaborate and solve solve problems that could not be solved by one system in isolation. Situational self-awareness is essential because of the problem with telemetry. There are delays. Information can be sent only like in bursts of data. There is delay when contacting a spacecraft, for instance, on Mars. So it's essential that this intelligent system detect a great deal of data, and they use it to correct fault detection, for instance, correct their own behavior autonomously, based on the heuristics and the guidelines that they have already acquired during the training phase when they were designed. And they're able to build new knowledge with their sensor information. And then we are at the end, so I'll just give a quick summary. So we started from the idea of artificial intelligence, what it is, and what it means for us. We talked about the discipline in the context of other disciplines. Then we talked about a little bit what we talked about in this presentation is, so the intersection of capability of human brain, current artificial intelligence technology, systems engineering, and the capability of an intelligent system to do foresight, decision-making, and classification, which are only some of the problems that can be solved by an AI. Then we talk about the necessity of observing the environment and be able to discretize the functioning of the environment or an event according to mathematical laws and convert all the information acquired into numbers, then be fed to the machine to be trained, for instance, with an artificial neural network. And then we talked about some of the space of the enabling technology for the use of intelligent systems in space, such as the autonomy or the ability to cooperate of small of different spacecraft. And are we going towards self-aware AI? At what point the complexity of these networks? Already during my limited experimentation with AI, I have seen that, by doing small, like university type competition with robots that need to chase each other, really when I uploaded the code on a robot, that sometimes would surprise me because it would start behaving with the other robots in the arena in unexpected ways. Just because the complexity of the code that just as a student I could create was such that didn't allow me to predict what the robot would do in an unexpected situation, and the ability of being surprised by an artificial intelligence. I mean, a very basic robot programming, is astonishing. So with all the level of complexity we've reached today, where are we really going? I will leave that to you to think about and to use the information I shared during this presentation to help in your pursuits and your studies. The last thing is about our books. So if you want to know more, we have 2 books coming. One is specifically on neural networks. So it goes from the very beginning to explain what a neural network is and how it can be implemented in your workflow from a systems engineering perspective. The other book is a simpler guide, a shorter book on artificial intelligence, and it's coming later on. Again, to merge systems engineering, which is, again, a very robust multidisciplinary approach. So to merge systems engineering and artificial intelligence. So how you can implement artificial intelligence to create smart systems. If you want to know more, register your interest for these books that are going to be published in collaboration with INCOSI, which is International Organization of Systems Engineering. You can go to our blog and register your interest. And then.
Thank you very much, Alessandro. So from my side, just to remind all of you, the possibilities to extend the training related to artificial intelligence at ispaceschool.com. Thank you very much.
Thank you for the attention.